I wanted to do some examples of some homework questions with you. These are some examples of the types of questions that I'll give you on your next assignment. This first question is asking about a one-sample t-test. And you can tell it's a one-sample t-test because a one-sample t-test is used to test if the mean of a population equals a certain value. And in this case, a researcher wants to test if the mean IQ of a population of college students equals 100. And you actually don't, in order to solve the problem, you don't really have to know that, in order to do a hypothesis test, you don't really have to know the size of the population. You don't have to know that it's 200,000, but you do have to know this number to answer a few of the questions that I've added in, that a few of the questions that are inside this question that I'm giving to you. But normally you don't need to know that number. Well, I mean, in a real life research situation, you wouldn't have to know this number. I also say that in this population, IQ scores have a normal distribution. That's another important piece of information. In the first question, in part A, I ask you what are the null hypothesis and alternative hypothesis of this study. In the one-sample t-test, the null hypothesis says that the mean of the population does equal the value being tested. So in this question, the null hypothesis would be the mean IQ score of the population equals 100. The alternative hypothesis is what the researcher is hoping to support or show evidence for. And the alternative hypothesis can be one of 3 different versions. And I can show you what the 3 versions are and how to select the correct one. The first version is the mean IQ score of the population is lower than 100. That's one possibility. Another possibility is that the alternative hypothesis could be that the mean IQ score of the population is higher than 100. The third possibility is that the mean IQ score of the population is different than 100. The first example is actually the alternative hypothesis of a left-tailed test. The second one is the alternative hypothesis of a right-tailed test. And the third one is the alternative hypothesis of a two-tailed test. So we have to figure out if we're doing a left-tailed test, a right-tailed test, or a two-tailed test to be able to figure out which example is our alternative hypothesis. This is the important sentence to look at. The researcher thinks that the mean IQ score of the population should be higher than 100. So this is what the researcher is hoping to back up. The researcher wants to show evidence that the mean IQ score is not equal to 100 and is actually higher than 100. And the alternative hypothesis is what the researcher is hoping to support, which is this second one right here. The researcher wants to support the claim that the mean IQ score is higher than 100. So this would be the alternative hypothesis in this question. And you wouldn't have to write out these other two. I would just want you to write out this version of the alternative hypothesis right here. So we're actually we're doing a right-tailed test, because if a person predicts, or if a person expects that the mean IQ score, the population mean, is above the value being tested, that's a right-tailed test. If the person expected for the population mean to to be below the value being tested, it would be a left-tailed test. And if the person simply wasn't sure whether the mean IQ would be higher or lower than this number being tested, it would be a two-tailed test. Question B says, draw the shape of the means of the possible samples, label the shape of the curve, also label the number of possible combinations of 100, and label the size of each possible sample. I might edit the wording of some of these questions to make it a little bit more clear, but this is basically my rough draft of this homework assignment. The wording will be pretty similar, but I might just change it a little bit. This is what I want you to do for this question. You can draw out a sketch like this. This is the wrong question. Okay. Draw the shape of the means of the possible samples. First, we have to know what the shape is going to be. So it says, in this question, IQ scores have a normal distribution in the population. The mean IQ scores of the 200,000 people in this population have a bell shape or a normal distribution. What that tells us is that the means of the possible samples will also be normal. If the population is normal, then the means of the possible samples also have to be normal. So we're going to draw a curve of sample means that has a normal shape. Just try to draw a bell curve like this. And on the number line, put sample mean, which means this curve is showing the means of the possible samples. And we know it's a normal curve because the question said that the population has a normal shape. So I just want you to label that it's a normal distribution. So you've already drawn the shape of the means of your possible samples, and we've labeled the shape because we said it's a normal curve or normal distribution. We need to find out what the number of possible combinations of 100 people would be, the number of combinations that might be selected from the population. To do that, we need to go to our combinations calculator. I have to go to Blackboard. You can see my announcements right here. My last announcement said that I'll create some possible exam questions soon, but I haven't created the newest sets of possible exam questions yet. Here we have our combinations calculator. number of things. This is asking for the size of our population. The question said we had a population of 200,000 people. Right here it says the researcher wants to test if the mean IQ of the population of 200,000 students equals 100. We also have to know how large our sample is. Right here it says the researcher recruits a sample of 100 college students. That's our sample size. So here we type in 100. We get our number of combinations right here. You can copy and, if you're doing, well, I guess you probably won't be typing your answer to this question, so you can't really copy and paste, but just copy down this number with the E plus, it'll say E plus something at the end. Copy the entire number with the E at the end, and this plus something, and then copy down this whole number in your answer. I'm just going to paste it in. So I could say you have this many possible combinations. And I probably want to draw an arrow to show that the combinations are inside of this curve in here. What else does the question ask for? The size of each possible sample. We've selected a sample of 100 people, which means our sample is one of these combinations of 100 inside of here. What I want you to do is fill in your curve with some boxes. Like this. It doesn't really matter how many boxes you make as long as you're filling in the area under the curve as well as you can. It might be easier to make the boxes first and then draw a bell curve around the boxes. And just write 100 inside each of your boxes to show that there's 100 people in each combination. So I would want to write 100 in each of these. Okay. That finishes, I think that finishes that part of the question, because we've labeled the size of each possible sample. We said that they're all 100. Question C asks you to draw the shape of the t-scores of the possible samples and label the shape of the curve. Now we need to actually find out what the shape of the t-scores will be. we know that our sample means had a normal distribution, which means that the t-scores of the combinations will also have a certain type of shape called a t-distribution. And a t-distribution is a little bit different of a shape than a normal distribution, but if you have large samples over 30, then it's pretty much a bell shape. The t curve is pretty much bell shaped. So just draw another bell shaped curve. Like this. And just make some more boxes. And then, well, this curve doesn't perfectly outline the boxes, but try to have it so the curve outlines the boxes. And then, if this shape was normal in question B, that means that this shape will be a t-distribution the shape of the curve will be a t-distribution with a certain degrees of freedom. In a one-sample t-test, the degrees of freedom are n minus 1, the number of people inside the sample minus 1. When you draw your diagram of t-scores, you want to label the bottom, the number line, with t-score instead of sample mean, and put 100 inside these boxes again. And then when the shape of this curve would be a t-distribution with 99 degrees of freedom, because 100 minus 1 is 99. Remember, in a one-sample t-test, the degrees of freedom is just n minus 1, or the number of people in the sample minus 1. In our question, data was collected from a sample of 100 people, a sample of 100 college students. So the degrees of freedom is just 100 minus 1, which is 99. That's the formula for a one-sample t-test. For the degrees of freedom in a one-sample t-test. What is it? Let's see what it asks next. Label the number of possible combinations of 100. The number of combinations will be the same. It's still the same number of combinations of 100. It's just now they're all stacked above their t-scores instead of above their means. So it's the same number of combinations. We'll put the same number here. Possible combinations. and draw another arrow inside of here. Show that those are the combinations. So we've already labeled the shape of the curve around the t-scores. We've drawn the curve. We've labeled the shape. We said it's a t-distribution with 99 degrees of freedom. We already wrote out the number of possible combinations. And since we put 100 inside each of the boxes, we labeled the size of each possible sample. So now we're finished with B and C. Question D says, can the one-sample t-test be conducted? As long as you have the correct shape around your t-scores, which is the t-distribution with a certain number of degrees of freedom, the one-sample t-test can be conducted. So since we had a normal distribution of sample means in part B, and we had a t-distribution curve in part C, because of the normal distribution in part B, this shape here led to this shape, and because we ended up with this shape in part C, that tells us that the one-sample t-test can be conducted. It can be conducted because we have the correct shape over our t-scores. So the answer is yes. What does the test statistic equal? We need the formula for the test statistic in a one-sample t-test. It's t equals the mean of the sample minus the population mean being tested over, sometimes, since it's the population mean being tested, sometimes it'll say 0 here, just meaning not a real population mean, but the population mean being tested, over the sample standard deviation over the square root of the sample size. Let's see what values we have. We have, our sample had a mean of, the mean of the 100 students in the sample was 106. That's our sample mean. Minus the population mean being tested. Population mean being tested, in this example, is 100. We're testing if the mean IQ score of this population is 100. So 106 minus 100 on top. On the bottom we have the sample standard deviation over the square root of our sample size. The sample standard deviation is 3.0, and our sample size is 100 because n is 100 because the researcher recruited a sample of 100 college students, which means the sample size is 100. You can see that right here. Let's solve the square root part first. On the bottom we have 3.0 over the square root of 100, which is 10. And on the top we still have 106 minus 100. On the bottom we have 3 divided by 10. 3 divided by 10 is 0.3. The top is 106 minus 100, which is 6. So we have to divide 6 by 0.3. We can do that with our calculator. Comes out to 20. It's a big number for a t-score. So for question E, we know our test statistic is 100, which is the test statistic, or the t-score, is 100. Now it says label the test statistic under the curve of the t-scores. Wait, was our test statistic 100? No, it was 20. Sorry. Let's go back to the curve we made for part C. We need to label our test statistic. 100 is actually way out here somewhere at the right end. So what are we? I would just put 100 way out here somewhere. If it comes out, no, not 120. Sorry, I keep saying 100. The t-score we calculated is 20. I would put it close to the right end of the curve since it's a large positive number. This is the t-score of 20. Right here. So we found the test statistic and we labeled it under the curve of the t-scores of the possible samples. What I'll also have you do is put an X showing where our combination is. Our combination ended up being one of these combinations with a t-score of 20. One of the combinations stacked above the t-score of 20 is what we ended up with. And let me try to do this a little bit better. Our combination is under the curve, so I'll try to make an X in this under the curve right here. If it goes a little bit higher than the curve, it doesn't really matter. I'll just try to put an X down here, showing this is where our combination is. So we found our test statistic. We've labeled it under the curve of the t-scores. We labeled 20. We're finished with part E. I mean, yeah, we are. This is actually part F, but I haven't changed it, corrected it yet. It says E again, but it would actually be part F. What does the critical value equal? To find the critical value, we have to go to a table, and I'll show you how to use that table. This is the t-table I was using before. We have to go up here at the top and choose one tail or two tails. And I'll show you how to know how you can figure out which one to choose. It depends on what alternative hypothesis we ended up with. These two versions of the alternative hypothesis that say lower or higher go along with one-tailed tests. These two are both one-tailed. When your alternative hypothesis ends up being this last one down here, it's a two-tailed test. And we knew that this was our alternative. We knew the middle one was our alternative because we looked inside the question and it said the researcher thinks that the population mean, should be higher than 100, which gave us this version of the alternative. Since we ended up with one of these two versions on top, we have a one-tailed test. So we're going to be using this row up here that says one tail. These numbers are the cutoff for the p-value, which means the cutoff for the maximum p-value you can have and still reject. Usually the cutoff is set at 0.05 in most studies, so we're just going to use 0.05 in this assignment. We also have to, so we're going to one tail 0.05. We also have to know our degrees of freedom. Our sample size was 100. We had 100 people in our sample. The degrees of freedom in a one sample t-test would just be 100 minus 1, which is 99. What you it doesn't, so we need to go down under where it says degrees of freedom and find out what our degrees of freedom are. You're actually not supposed to go up to a higher number than what you have. So if we have 99 degrees of freedom, we're really not supposed to use 100, but we should use 80. But for this assignment, I'll just have you round, either round up or round down to the closest one. If you end up with a number like 34 degrees of freedom or 32, you can just use that row for 32. But we have 99, so we need to round to 100. We have one tail, 0.05. Let's go down to 100. It's 1.66. One tail, 0.05. And with 99 degrees of freedom, which is close to 100, the critical value is 1.66. What else does it say? Label the critical value in the sketch of the t-scores. 1.0 is in the middle right here. 1.66 is a little bit higher than 0. So 1.66 would be about right here. Or maybe a little bit higher. Maybe right here. When you're doing this assignment, it might be easier if you make tick marks under here, such as 0, 2, 4, 6, 8, 10, or 0, 5, 10, 15, and 20. That way, you know exactly where to put 1.66 and where to put 20. But I'm not going to mark it off if it's not in the exact right place in this number line. So here's one. I'm saying that this is 1.66. I labeled the critical value. Now it says label the rejection region and label the percent of possible samples at or beyond the critical value. So the rejection region is the entire area that's beyond, it's at 1.66 or beyond. So you can draw a dotted line and then draw an arrow inside here and say that this is the rejection region beyond the critical value. So this still says part C, but in these other questions, you're just adding new things to the curve that you already made for part C. I mean, you're adding new things to the sketch that you already made for part C. What does the next part say? Label the percent of possible samples at or beyond the critical value. It means label the percent of combinations in the rejection region, which is, you could just say, after the rejection region, you could say 5%. Rejection region, 5%, like that. What does the p-value equal? And draw a sketch of the p-value under the curve of t-scores and label the p-value. Let's see. I'll have you use a website, it's a p-value calculator. We're doing a t-test, so we go to where it says p from t. We enter in our t-score, which was 20. We enter in our degrees of freedom, which was 99, because the degrees of freedom is our sample size minus 1. T-score of 20 with 99 degrees of freedom. Let's see what it says. Less than 0.001. The small p-value. Um, what I actually want you to do is don't make this, where you label 20, try to make the curve go a little bit past your test statistic of 20, or make sure it goes at least a little bit past what your test statistic equals. Because our t-score was 20, and what our p-value is the percent of outcomes or samples at or beyond our t-score of 20. So you need to have a little piece that you can shade in here. And this is the p-value that we've shaded. Yeah, this line here is supposed to be 20. It's supposed to be at 20, so the p-value is this area. The p-value isn't the same thing as the rejection region, because the rejection region is the total area at the critical value from the table and over to the right. It's the area from this, starting at this dotted line and going over to the right. P-value is the area or the percent at your test statistic of 20 that you calculated and further to the right. So the p-value, when I say a p-value is a percent, it's really a percent written as a decimal. So if the percent is 20, the p-value is 0.20. Draw a sketch of the p-value. We just shaded it, so we have a sketch. Label the p-value. You can say that this is the p-value with an arrow pointing to it. And you can say it's less than, if the question said less than 0.001, I mean, if that's what the calculator says, put a less than sign and then put 0.0001. So there's the percent of samples that are in this area out here is actually a very small percent. So we finished that. This says, can the null hypothesis be rejected? That depends on a couple of different things. Well, I mean, there's two different ways to check whether the null hypothesis can be rejected. Oh wait, first, for question F, I forgot to say what the p-value equals. I labeled it in the sketch, but I didn't put my answer in here. So the p-value is less than 0.0001. You can reject the null hypothesis if the test statistic, your t-score, is at the critical value or higher. And our test statistic that we calculated ended up being 20, and the critical value is 1.66. So our test statistic is equal to or greater than the critical value, meaning it is in the rejection region, which would mean that we can reject the null hypothesis. The other way to check is looking at the p-value and seeing if the p-value is 0.05 or lower. And the p-value is 0.05 or lower because it's less than 0.0001, which is it's definitely less than 0.05. So you would say yes, because the test statistic is equal to or higher than the critical value, and the p-value is at 0.05 or lower. This says, can the researcher claim that the mean score of the population of college students appears to be higher than 100? Meaning, did the researcher support did they ended up supporting what they were hoping to show evidence for? The null hypothesis said that the mean IQ score of in the population equals 100. And we know that the null hypothesis was rejected because of our test statistic and p-value, which means we're rejecting this possibility. If we reject the null hypothesis, we're going along with our alternative hypothesis, which said the mean of the population is higher than 100. So we rejected the null and we did support the alternative. We did support the possibility that the mean is higher than 100. So the answer would be yes. What this means is that we know that our sample mean came out to 106, which is higher than the population mean being tested. And our sample mean of 106 did give us good evidence that the mean of the population is higher than 100. What I also will have you do for this question is, well, first I wanted to say, if this sample mean didn't come out above 100, we would have a problem, because we're hoping to show evidence that the mean IQ is higher than 100. If this sample mean came out to a lower number, like 95, you actually wouldn't be able to run the test with this alternative hypothesis, because if the sample mean comes out lower than at 100, it's not possible for your data set to support the possibility that the population mean is higher than 100. The only way that you can support this alternative hypothesis right here is if your sample mean comes out above 100, which it did in our example. If our sample mean came out to 95, we would have to redo our plans, and we wouldn't be able to use this alternative hypothesis anymore. That's not really going to be an issue in this assignment, but I just wanted to let you know about it. I also want you, in part B, where you draw the shape of the means of the possible samples. I want you to label the null value, which is at the center. In a one-sample t-test, the null value is the population mean being tested. We're testing if the population mean is 100. We're testing if the mean IQ is 100. So 100 is our null value right here. So I'll have you label this in part B. That finishes that question. This is another version of the same type of question. It says a researcher wants to test if the mean IQ of that same population equals 100. But in this question, it says the researcher thinks that the mean IQ score, the mean IQ of the population is lower than 100. Everything else is still the same. The researcher recruits a sample of 100 students, and, well, actually, it's not totally the same, because the mean of the 100 people came out to 96 in this example. What's the null hypothesis? In a one-sample t-test, this is another one-sample t-test, because you're testing if the mean of the population equals a certain value. It says that the population mean, or how did I write this last time? The mean IQ score of the population equals 100, because the null hypothesis just says that the population mean does equal the value being tested, and we're testing if it's 100. I said that there was 3 different versions of the alternative. Last time we picked the choice that said the mean IQ score is higher than 100. Now we have to figure out what it's going to be this time. This says the researcher thinks that the mean IQ score of the population should be lower than 100. So the researcher is trying to support the idea that the population mean is lower than 100, which means the alternative is the possibility that the researcher is trying to support. So the alternative would say population, the mean IQ score of the population is lower than 100, or less than 100. Then it says, draw the shape of the means of the possible samples, label the shape of the curve, the number of combinations of 100, and the size of each sample. This is just doing part B all over again. You'll do it the same way you did here. You have to figure out what your shape is, what the shape of the sample means are. We can figure that out by looking inside the question. It says, IQ scores in this population have a normal distribution, which means that the sample mean curve will be normal. So once again, we'll be drawing a normal curve around our possible samples, and you'll say it's a normal distribution. You'll find the number of possible combinations with the combination calculator. Inside each box, you'll put the sample size. Our sample size is 100. It's still 100 because the researcher is recruiting a sample of 100 college students. Sometimes it might be another number. For example, if it said 50, you would put 50 inside each of those boxes instead of 100. You also want to say sample means down here and label your null value, which is the population mean being tested. The null value goes at the center of this curve. What's our null value? We're testing if the population mean is 100 in the first sentence. So we're testing 100 as the population mean. That means that the null value is 100. So we would put 100 as our null value in the center. And that pretty much finishes part B again. Part C says, draw the shape of the t-scores of the possible samples. Label the shape of the curve, the number of possible combinations, and the size of each sample. It's the same thing part C is the same as it was before. All you do is draw a t-score number line, stack some boxes above it like this. What do you have to do? Label the shape of the curve, like we did last time. If the sample means ended up being normal in part B, then you'll end up with a t-distribution curve in part C. So you'll label t-distribution with a certain number of degrees of freedom, which is the sample size minus 1. It's still going to be 100 in this question because we recruited 100 students, so it's 100 minus 1. So we know what the shape is. We labeled the shape of the curve. We labeled the number of combinations, and we labeled the size of each sample when we put the sample size inside each box. Questions B and C work the same way that they did in the last question we did. Can the one-sample t-test be conducted? Our sample means had a normal shape in part B, and we knew that the sample means had a normal distribution because the question said it said that in the population IQ scores have a normal distribution, which is telling us that the sample means are also normal. Since the sample means are normal, the t-scores follow a t-distribution with a certain number of degrees of freedom, and that means that the test can be done. If the t-scores have the correct curve around them, the test can be done. So the answer would be yes. It says, what is the test statistic equal? You'll use the same formula that you did in the other question. What numbers do we have this time? We have the mean of the sample is 96 with a standard deviation of 2. So we have 96 minus 100 over our standard deviation, which was 2, over the square root of our sample size, which was 100. Or which is 100. We have the top is negative 4 because 96 minus 100 is negative 4. The bottom is 2 divided by 10, which is 0.2. Let's see what negative 4 divided by 0.2 equals. Comes out to 20 again. Except this time, the top came out negative 4, which means the t-score will be negative 20 instead of positive 20. The test statistic is negative 20. It says label the test statistic under the curve of the t-scores of the possible samples. This time we're not labeling we're not going to be labeling it at the right end because it's a negative number. So all of this will be changed. This is no longer our rejection region. Our t-score ended up being down here at the negative end, at negative 20. And if we want to put an x where our combination is at, we just put an x right above 20 under this curve. Maybe a small x right here. Now what do? We labeled our test statistic, so we're done with this question. What does the critical value equal? Well, first we have to use that critical value table again, and we have to know if we're doing a one-tailed test or a two-tailed test. Remember, both of these alternative hypotheses right here that say lower or higher or a one-tailed go along with a one-tailed test. And our alternative said way up here said the mean IQ score of the population is lower than 100, which means we're doing a one-tailed test. So we go back to our critical value table. We go to one tails 0.05 up here, and we go down to our degrees of freedom. Our degrees of freedom in this question is still 99 because I'll actually stop this recording and start it right where I left off.